So all of this is to get to a point where we can estimate the boundary layer thickness, which eventually, as you'll see, is going to help us estimate the heat transfer coefficient. For now, if we can just develop this model that lets us estimate the boundary layer thickness, that'll be sufficient for what we're trying to do. So if we're going to estimate the boundary layer growth, I've already mentioned this idea that this thermal wave is propagating, and it's basically the same idea as the 1D conduction problem. So let's remember back to this thermal wave depth for 1D conduction, where we're estimating this depth to be approximately 2 times the square root of alpha t, where you just let some amount of time elapse. So if we think about this problem, where we have now we have some plate and fluid is coming across it, and that fluid is taking time. It's sort of moving, and the boundary layer is forming. And as you sort of trace along in time, if you allow some amount of time to elapse, basically that corresponds to a position, right? And you now allow another amount of time to elapse, and that's another position. So there's a direct relationship between time and position, and that relationship is the velocity of the fluid, or the free stream velocity. So here, let's just say that time is actually equal to the position divided by u infinity, right? Meters over meters per second gives you seconds. So that gives you a time. And let's substitute that in. So delta t is approximately equal to 2 square root alpha times x over u infinity. So now we have a model for how the thermal wave depth is going to grow as a function of coordinate x. This is true for the thermal part of the problem, but we also maybe want to think about the momentum boundary layer. So for the momentum, that's going to be delta m is approximately equal to 2 times the square root. So let's stop for a second. Alpha is the thermal diffusivity, right? This is K over rho C. This is a measure of how easily heat propagates through some medium. There's an analogy for that in the velocity or momentum domain, and that is the kinematic viscosity. So this nu, I'm going to write it like this, so note the double hat. So nu is equal to mu over rho. That's our kinematic viscosity. And so kinematic viscosity is the analog for thermal diffusivity, and in fact it has the same units. It's meters squared per second. So we plug that in, so it's nu times x over u infinity. This gives us the momentum boundary layer growth. So this is all maybe helpful. It now gives us this estimate of the boundary layer thickness as a function of position. But it also introduces this new idea that we need to define called the Prandtl number. So the Prandtl number, abbreviated PR, is a ratio of two things. Just like if you remember fluids, the Reynolds number. The Reynolds number is a relationship between inertia and the shear stress. Here, Prandtl number is basically the ratio of transport of momentum over the transport of heat. Right? And using these ideas that we've just identified, the ability to transport momentum, well, that's captured by delta m. Right? That's a relationship of the ability to transport momentum. It's the boundary layer growth in momentum over delta t, which is the ability to transport heat. Now it turns out that the relationship that's used here is actually delta m over delta t squared. So that is the definition of Prandtl. But it's basically this ratio of these two things. So we can plug this in and kind of simplify down what we have here. So Prandtl is equal to 2 times the square root of nu x over u infinity over 2 times the square root of alpha times x over u infinity squared. Okay, so that actually gives us, simplifies down, the 2's cancel out. We're left actually just with nu over alpha, which if you express this ratio in terms of the original parameters, turns out to be mu times c over k. So let me write it here. Prandtl equals mu times c over k. This is a property of the material, right? It's a property of the fluid. So the ability to transport momentum and the ability to transport heat depend on viscosity, heat capacity, and conductivity. It doesn't depend on the flow conditions. It doesn't depend on really anything else except for what these properties are. So we can look at the relationship between the boundary layer and both the thermal side and the momentum side for these different cases. So let's say we have some kind of a fluid where conductivity is extremely high, but viscosity is much lower. So say maybe this is like a liquid metal where it's flowing, but the conductivity is extremely high. So that's going to be a case where the Prandtl number is less than 1. So we could sketch out for this what the boundary layer growth looks like. So let's say this boundary layer here is delta T. Now let's sketch out delta M, right? These boundary layers can actually grow at different rates, right? Heat is going to be transported at a different rate than viscosity is, momentum is transported. So if Prandtl is less than 1, that means it's easier to transport heat than it is to transport momentum. And so the boundary layer for momentum is going to maybe grow like this, delta M. If Prandtl is greater than 1, then you're going to see the opposite occur. Right now, where this is delta M, and this is delta T. And if Prandtl is exactly equal to 1, then the boundary layers just grow at exactly the same rate. So these different scenarios maybe help you conceptualize like what's happening in the boundary layer. There can be two different growth rates for momentum, that is the velocity profile, and for heat, which is the temperature profile. Those can develop at different rates, and the rates are governed by the Prandtl number. So all of this is fine, but it doesn't really help us yet estimate what we really care about, which is the heat transfer coefficient. So let's now tie this back to the heat transfer coefficient using an approximate model. So the first thing that I want to point out is that if we have a relationship for heat transfer, Q dot double prime in the y direction, in laminar flow, Q dot double prime y is conduction. So let me just unpack that a little bit. In laminar flow, what we mean is that if you look at the flow over a plate, so say this is our plate here, if you look at the flow over the plate, the velocity profile might look something like this. But note that the vectors for, these vectors here are pointed in only the x direction. There is no significant component of velocity in the y direction, right? This doesn't exist. Now for turbulent flow, where you'll get into this, but the flow is kind of all over the place, then you have to deal with the y component. For laminar flow, and the idea behind the word laminar is that you just have sheets, right? These are like laminations or sheets of fluid. They all exist in a single plane. They're moving on top of each other, sliding over the top of each other. So the only way for heat to move in the y direction is by conduction between these effectively sheets of liquid. So realizing that, we can write an expression and write it in terms of conduction, right? This becomes purely a conduction problem. So our problem here is Q dot double prime y is governed by Fourier's law, which is minus k dt dy. And then let's get an approximate model for this, right? This is the actual equation in terms of a partial differential. Let's estimate the dt and the dy part based on our boundary layer problems. So here, let's estimate this as conductivity. Now, because we're taking delta t over delta y, we're going to, the negative sign goes away, right? But we end up with an estimate for delta t, which is, let's just write it this way first, delta t over delta y. So Q dot double prime y is approximately equal to k times what's our estimate of the temperature difference? Well, that is going to be Ts minus T infinity. That's the total temperature difference across the boundary layer, right, from the plate up to the fluid. Well, what's the delta y that goes with that? That's going to be delta T as a function of x, right? That boundary layer thickness, which is varying as a function of x. So maybe stop for a second and look at this. We now have a relationship for Q. We have a driving temperature difference here, and then we have some other stuff multiplying it here. So this is effectively like saying Q dot double prime equals approximately equals Ts minus T infinity over R. And we know that R convection, right? R convection is equal to 1 over H bar A. In this case, we are expressing this in terms of the double prime, right? So this area term goes away. So what we're saying here is basically that our estimate for H bar is related directly to conductivity and the boundary layer thickness. So this would be saying H bar is equal to K over delta T, but it'd have to be delta T bar, right, the average boundary layer thickness. Or what we can say is, well, I'm actually just going to compute the heat transfer coefficient H at some coordinate x. And so that's going to be approximately, here's approximate as well, approximately equal to K over delta T at whatever the coordinate x is that we care about. So this is maybe our first insight to what we actually mean by heat transfer coefficient. What the heat transfer coefficient is a relationship between the fluid properties and the boundary layer thickness. The fluid property being the conductivity, and the boundary layer thickness relating to the propagation of heat as it's conducting into that fluid. As the boundary layer grows, then you're going to see, right, as this boundary layer thickness grows, you're going to see Hx decrease. So there is a relationship between the position on this plate and the local heat transfer coefficient. So maybe let's plot that out just to kind of understand what I mean. So here we've got something, these quantities that we're plotting as a function of x. So first I'm going to plot the local heat transfer coefficient, h of x. So I'll do that in the color green. So h of x, as we go to the beginning, the kind of start of the plate, and we just scroll up. At the very leading edge of the plate, what is the boundary layer thickness? It's actually 0. So at the leading edge of the plate, there's an infinite heat transfer coefficient. Right? So all the way up, there's an infinite heat transfer coefficient. But as it develops, that boundary layer thickness grows, and you start getting this curve like this. So this is Hx. We can sketch out the boundary layer that goes with that, right? So that's going to look something like this. This is my delta T as a function of x. Likewise, we're talking about heat transfer coefficient here, but you can do the same thing for the momentum boundary layer. The momentum boundary layer, let's say, looks something like this. Delta M, it's a function of x. And there again, the shear stress right at the leading edge is infinite, at least according to our conceptual model. And you would get some curve that sort of mirrors like this. So this is tau as a function of x, or tau at a position x. So this is kind of the way that the heat transfer coefficient and the shear stress are computed in terms of the boundary layer thickness. So now we've developed this model for heat transfer coefficient, which is a function of x. And what this is telling us is that at a specific location on this flat plate, there is a heat transfer coefficient, and that thing is changing. That heat transfer coefficient is changing as a function of x. So eventually we would need to, if we wanted to compute h bar, which is the average, we need to take the area average integral, which we'll get to in a little bit. But for now, we've developed this, assuming this delta T model or delta M model, which is a really approximate model. The so I want to get to a point where we can actually have the exact model for that, so you can compute the heat transfer coefficient more accurately. However, the correlations that express the delta T are often done in terms of the Reynolds number. And so first we need to kind of transform our delta T equation into something involving a Reynolds number so that we can then use kind of the standard form.